Good morning. This is Larry Olson, President, Chief Engineer, and Founder of Olson Engineering and Olson Instruments. It's my pleasure to welcome you today to my second seminar or webinar that I'm giving on non-destructive evaluation of concrete dams. I'd like to thank everyone for signing up, and hopefully you learned something out of this and can appreciate how the non-destructive evaluation can work for you on your dam projects. No pun intended. So, having said that, we will be sending out, after a bit of cleanup, a link to the video today on YouTube, and there'll also be a PDF copy of the slides that you'll see available for download as well, either directly from our website or there'll be a link from YouTube. So I do want to thank everyone for signing up, and hopefully you can learn something that's very beneficial out of it. Having said that, I'm going to go to the slideshow, and we'll finish in about an hour. Okay, so in a simple sense, a little bit of a saying we use is beyond visual. So today we're going to be talking about not only is visual quite important, but to do non-destructive evaluation to see the interior of the dam and the conditions of such other facilities as spillways and conduits on dams. Just some references on NDT methods for estimating in-place concrete strength. I'm a member of this ACI 228 non-destructive testing committee. There is a committee report on methods for estimating in-place concrete strength. And they're listed there. Some of those you're probably familiar with. We'll be talking a bit about ultrasonic pulse velocity. We have used that when correlated with cores tests and laboratory tests of strength, and along with surface waves to estimate in-place dam strength when it was needed. The second document that's useful, and almost all the methods we'll be talking about today are discussed in this document, is the 228 report on non-destructive test methods for evaluation of concrete and structures. Again, the bolded methods are the ones that we'll be showing in case histories on the dams today: ultrasonic pulse velocity, impact echo, stress wave methods, surface wave methods, as well as infrared tomography, ground penetrating radar, and some sonic ultrasonic velocity and tomography. So I think most people are probably aware of the basic wave types because of earthquake engineering and designing for earthquakes. But I will mention at least that when you impact the surface, you generate a primary or compressional wave. That's the fastest wave. The secondary or shear wave is the second wave generated. And the strongest energy, that's about 26% in shear waves, 7% in compression waves, and 67% or 2/3 is a Rayleigh or surface wave. It has the most energy from that impact. So to visualize this, a compressional wave will, as it propagates, will compress and extend as it passes through a medium. A kind of a push-pull action. The shear wave, you could think of this like a earthquake fault shearing, has a shearing component. We primarily use shear waves in earlier. Dr. Ryan North and Travis Nielsen with our company gave a webinar that's also on the YouTube site on seismic testing. And we use shear waves in seismic testing for getting the shear modulus as well as related Young's moduli. And finally, a Rayleigh wave. As it propagates along, it's going to the right. The particle motion at the surface is what's called a retrograde elliptical motion. And that has a very strong component vertically, and that's what we measure as it passes by our receivers, as we'll talk about. So relative speeds for concrete with a Poisson's ratio of 0.2, the compression wave velocity would be 1, the shear wave velocity is 62% of the compressional or primary wave, and the Rayleigh wave velocity is 10% slower than the shear or 56% of the compressional wave. So the case histories we'll be talking about today will include impact echo for concrete, cracking, thickness, and integrity. One-sided tests, spectral analysis surface waves for freeze-thaw cracking and alkali silica reaction cracking, and concrete masonry quality, as well as correlating to strength when you crush the cores and do pulse velocity testing as well. Sonic cross-dam tomography for imaging internal conditions of concrete and masonry dams. Slab impulse response testing for voids, subgrade support evaluation of spillways and behind conduits. Generally done in conjunction with ground penetrating radar to also evaluate typically void subgrade support conditions, but also to map out steel reinforcement mapping. So literally map out the steel reinforcement in the structures where it is reinforced. Finally, we'll close with infrared thermography, which is useful when you have shallow delamination, say of a repair or something like that, that will map that out fairly quickly. So the impact echo test, there's an ASTM standard for it, and it's also discussed in the ACI 228.2 document. The test involves impacting the surface of the concrete, looking for resonant echoes from either a crack or planar like void, a plane of void, or a full thickness echo. That time domain response, because it's a resonance test, is not so clear, but by going with the fast Fourier transform to the frequency domain and you get a displacement spectra, you get a distinct echo peak at a frequency. That depth of that echo is equal to this shape factor, which is 0.96 for a slab or wall shape. It's a lower number for a beam or column shape, but there's one dominant echo in a flat slab or wall or a spillway, where there are multiple resonances present in beams and columns because of the shape effects. That's multiplied by the compressional wave velocity divided by twice the frequency of the resonance. So in a simple sense, if that was a 6,000 hertz echo and it was 12,000 feet per second factored impact echo velocity for the concrete, then you would say the depth equals 12,000 divided by 2 times 6,000, or it's a 1 foot thick echo. A 12,000 hertz echo would be a 6-inch echo. So this shows some of the test equipment we've developed and used as Olson instruments and in our consulting work. This is a handheld solenoid impactor with a displacement transducer that's pushed against the concrete, and that'll work out to maybe up to about 2 feet. You can use a hammer, so from nominally 3 inches to 2 feet, although someplace around 18 inches, we often switch to a small hammer. And you can use a larger hammer to get out to approaching 2 meters or 6 feet. We have a waterproof version for specialized underwater testing. We've used in consulting on canal linings and bridge piers with divers. So the first case history of a dam I was involved in was back in the 80s and testing on a mountain dam in Colorado. They had extensive freeze-thaw cracking damage and they wanted to map out the extent of it. Here's a downstream view of the dam looking up at it. It's in a canyon. A portion of this dam was generally in the shade, so less freeze-thaw cycles in the wintertime. Another portion was out in the sun with more freeze-thaw cycles. So this is the view. We were hoping to test it in early fall. Instead, we got to test in November when it got to -11 at altitude around 10,000 feet. And the crest of the dam is shown here. The equipment was up here. It snowed during that time, but the toughest job was the climber that we sent over the edge to do the impact echo testing. So at that time, it was an accelerometer held in contact with the concrete, and that instrumented its impact hammer to see if we were seeing multiple echoes from shallow cracking damage in the first several feet of the dam. So this is an example of that result, when the impact echo resonances are clear with multiple peaks, indicating there was multiple levels of cracking, with some contact nonetheless, but still multiple levels of cracking. It was cored, and when they cored it about 3 feet in, they quit coring because too much water was coming out and nobody wanted a giant ice waterfall in the dam for the rest of the winter. So they were fortunate we were able to plug the hole. This just shows some calibration testing on a small piece of the core. Most of it was broken up from cracking, and we got a velocity from that as well to calibrate our results. So impact echo and other non-destructive evaluation methods can be used to look at concrete conduits. They're often lined with steel in dams, and you can test through the steel with impact echo and some ultrasonic pulse echo techniques for checking the steel itself. So here, I was personally testing this one several years back with a small hammer and the handheld instrument to see thicker, because it was nominally 2 feet thick behind this 4/10 of an inch thick steel lining with concrete on the outside. So this shows an impact echo test result. The top is time versus voltage. The resonant response there shows up as a peak here that corresponds to 25.7 inches for typical concrete velocity of 12,000 feet per second for impact echo. So that's a sound result. Another area had a problem, and most of it was well-bonded steel, but this ringing result indicated a void condition, that it was not well-bonded from the steel lining to the concrete, and it was just ringing with a high amplitude result, and couldn't see the echo, but we did know there was not contact with the steel pipe lining at that point with the concrete. We also checked for corrosion by doing ultrasonic thickness pulse echo testing with a 5 megahertz probe. You get an echo on the screen of the instrument, and we found variation in the steel lining thicknesses of that pipe ranging from 0.34 to 0.52 inch to evaluate whether the corrosion was becoming a significant problem or not. I believe in this case it was not yet a significant problem. So the second test we did on that project was spectral analysis of surface waves. This test involves striking the concrete again. I'll give credit to Professor Kenneth Stokey at the University of Texas at Austin and his subsequent students. I studied under Ken for my master's in geotechnical in the late 70s before going into practice for 5 years as a geotechnical materials and pavement consulting engineer and starting my own practice in 1985. But what he had come up with was the idea of looking at surface waves with more sophisticated measurement and modeling to, from the surface, determine the variation of shear wave velocity versus depth for soil sites. It's been expanded to pavements and structures, and also it's evolved into the multi-channel analyses of surface wave methods. It's a similar physics. But here we're showing two receivers on a bar held in contact with the concrete, hitting it with a small hammer to generate the wave energy, recording it with our Freedom Data PC, and the physics that we are depending on, if you remember freshman physics, is velocity equals frequency times wavelength. So this just shows the equipment up close. There's a displacement transducer. They can vary in spacing on the bar from quite close at 6 centimeters out to 80 centimeters or 2.62 feet. So going from just a few inches to see very shallow and out larger to see up to 7.5 feet deep. If you need more flexibility, you can use small accelerometers, typically magnetically coupled to washers and grease mounted on the concrete. That allows you to have even wider spacings for more distances. The wider you are apart with your receivers, the deeper you can see into the concrete. And you can take the data with either the Freedom Data PC with many tests and a number of tests on a smaller handheld unit that we call our NDE 360 platform, which has a touch screen and compact flash. But the PC is Windows-based. Both of them will last all day in the field. So some example data is showing time versus voltage of the two receivers. And the big spike on the left is the surface wave energy. That's the most energy. So you can window in on that and process it with the software to produce what's called a phase plot. So this shows signal coherence from 0 to 12,000 hertz, 13,000 hertz. When that's near 1, it's good quality data. At higher frequency, it's starting to drop off, but the phase still looks pretty good. These phase cycles, this is called wrapped phase. It goes from 0 to minus 180. It jumps up, comes back down, and at 2628 hertz, that shows that the response of the far receiver is one wavelength lagging the response to the surface wave energy of the closest receiver to the impact. So the math is, in a simple sense, that for this spacing of 2.62 feet, that's one wavelength. Velocity equals frequency times wavelength, multiplying times the spacing on the bar gives you 6,900 feet per second. So this phase plot goes from at high frequency short wavelengths to longer wavelengths of 5 feet or more at the low frequencies. That's all plotted as a dispersion curve or surface wave velocity versus wavelength. And the signal coherence again is shown, but the bottom plot is showing here's 8,000 feet per second, here's 0 on the surface wave velocity. Wavelengths going from basically 0.8 feet for that wide bar spacing up to 5 feet, and it's nominally 6,900 feet per second. Very uniform concrete, no damage. So here, back testing on this outflow pipe wall of a dam, looking for voids as well as general concrete quality, the velocity and modulus of the concrete behind the pipe lining, holding the bar in place, hitting in line the close receiver, receiver 1 and the receiver 2 further away to do the testing. So because the steel is fairly thin and where it's bonded, you can get pretty good test results. This shows a good overlay of the software. The phase plot is shown in the bottom. You can see a number of phase cycles that are pretty clean. And that's plotted in the upper left as velocity versus wavelength, the dispersion curve. Nominally 7,300 feet per second on average, a little slower near the surface, but then pretty consistent. So this is good quality concrete, as it's 56% of the compressional velocity. Shear waves, surface waves are typically in the range of 6,000 to 9,000 feet per second. Can be a little slower or faster depending on the concrete. Faster is stronger, higher modulus concrete. So this is a result from an area that had some issues with void intermittent contact conditions. It was fast near the surface, but then it dropped off, showing slower velocity results. You can see how the phase curve is not as many cycles. It's gotten slower at the longer wavelengths going out to 3 feet. So you definitely get variation in the results depending on the concrete integrity. And it can be affected by both cracking damage and alkali silica reaction or freeze thaw. So this is testing on a dam project, again with a climber. You can see I don't know if I want to call it convenient, but you can hand hold the SASW testing bar, 30 feet, 80 centimeters. You would be hitting to the right of it or the left to get the velocity of the surface wave with depth. And by doing that, we're able to determine the competency or soundness of the concrete. It'll be fast when there's a lot of freeze-thaw damage or even alkali silica or alkali aggregate reaction. The wave velocities will be slower and it'll show up in the data quite clearly. So here's example results again of the velocity versus wavelength plots. On the left is sound concrete, wavelengths shown of about 4 feet deep, starting from about 4/10 of a foot, and nominally 6,500 feet per second. By comparison, this was done on a patched area on the dam. The surface patch started off being much faster, but quickly got slower and cracking damage. And then at about 3 feet in, a wavelength of 3 feet, the velocity starts to increase, indicating the depth of freeze thaw cracking behind the patch is about 3 feet deep. So when you do this on a grid, you can plot up with a color scale the depths of freeze thaw cracking damage. And for this dam, with the scales in feet of the depth down from the crest and across the crest on the downstream face, we're showing shallow freeze thaw cracking damage from 0.2 feet to 1.4 feet. Now, obviously, coring is necessary and maybe petrographic examination to make sure it's freeze thaw cracking damage as opposed to alkali silica or alkali aggregate reaction. So coring is still definitely done for confirming the results, as you'll see. So one of the first applications of spectral analysis surface waves, where it was very useful, was on this old dam built around 1910 near Big Rapids, Michigan. It won an award from the International Concrete Repair Institute in 1996 for the engineering team that investigated it. The problems were, and let's just talk about the old style dam for a second. These are tainter gates, as many of you know. Here's the abutments, the piers, the weir, some interior rooms underneath it, and most may not know what this is. The best guess is it's a fish ladder, but in 1910 we weren't so worried about fish. It actually was designed as a log chute. So the logs floating down the river could go off towards the sawmills to help build Chicago. So that's basically the old dam. Now the problem was they had done a repair in the late 80s, I believe, and then a few years later, the shotcrete that they had sprayed on was debonding and cracking severely, as you can see here at this picture of the pier near the tainter gates, one of the tainter gates. This happened because, unfortunately, not enough of the original freeze-thaw cracked up concrete was removed, nor was the shotcrete repair permanently or positively doweled into the existing concrete. The result was it wasn't well bonded, and within 3 years, it was debonding severely. So when you impacted it with a hammer, you'd often hear a hollow drummy sound for shallow debonding the shotcrete. Interestingly enough, they had taken 50 cores, and even after 50 cores, they weren't satisfied that they fully understood the extent of the damage and if they could repair it or not, because they almost had to repair it, otherwise they would lose the dam because the permitting process would not have permitted it. So they wanted to keep producing power, keep the dam, and repair it. So they got us involved to do spectral analysis surface waves and impact echo and some pulse velocity testing of cores. So here shows a SASW test using those accelerometers where they're magnetically coupled to washers that are coupled with a lithium grease to the surface. And we could spread these accelerometers out to 5 feet when here it's about a foot apart, when the abutments got to be as thick as 9 feet. The piers were typically 5 foot thick, but the abutments near their bases were quite a bit thicker. So this old slide is a little hard to see, but hopefully you can see the surface wave velocity is going from 0 to 10,000 feet per second. The wavelengths on a logarithmic scale are 1/10, a foot, and 10 feet. The white dots are data from testing in 2 directions with the SASW test, forward and reverse. And so it starts off at fast velocity, but at about 3/10 of a foot, the white dots drop from around 9,000 feet per second all the way down to an apparent velocity at a 2-foot wavelength of 4,000 feet per second, and then it starts to increase. So what that means is there was the sound shotcrete over freeze-thaw cracked original concrete over sound deeper concrete, which was good news. We fit that with a theoretical dispersion curve model with the open squares, and from that modeling, we produce this plot of shear wave velocity, which is 10% faster than the surface wave, from 0 to 5 feet on this particular location on the abutment wall, showing 3/10 of a foot of fast shotcrete, 9,000 feet per second, dropping down to 2,500 feet per second of freeze-thaw cracked concrete, and then jumping up to 8,000 feet per second. So this was compared with coring results with good correlations. We mapped it out throughout the rest of the dam on a grid basis, and the project went on to be successfully repaired. We also did some impact echo results just to show that to you briefly again on these old plots. There's multiple echoes in a cracked area, as you can see on the left plot. In the sound area, that was an interior wall that was more protected from freeze-thaw effects underneath, so to speak, the gates. You had a sound echo predicting 2.7 feet, which was correct. So this is just showing a single echo, sound concrete, versus multiple cracked echoes in the freeze-thaw cracked concrete. So shifting gears a bit, we'll start talking about ultrasonic and sonic pulse velocity tests, and generally done on dams for tomography purposes. Tripping over my tongue, for velocity tomography testing. So on the left are some of you may have seen the 2-inch diameter, nominally 50 kilohertz ultrasonic transducers that would send out a signal at resonance and receive it a known distance away, grease coupled on the concrete, or testing cores in the lab if you want to develop correlations of strength and velocity. So when you get into dams in larger structures like bridge piers, they can get so thick that you can't send the ultrasound more than, say, 5 feet readily. Sometimes we've gotten it to go 9 feet in sound concrete, but typically you run into issues if you have any damage at all, getting it to go much over 5 feet. So then we do what's called a sonic pulse velocity test. Lower frequencies could be a fairly small hammer to starting off at 0.2 pounds with an instrumented load cell built in to measure the impact force and timing. And then a receiver. It could be an accelerometer. It could be one of the ultrasonic pulse velocity transducers as well. Or getting up to a 3-pound hammer. We often use a 3-pound impulse hammer with a hard plastic tip on dams, as you'll see. So there is an ASTM standard for this as well, and it's also in the ACI 228.2 document. But here is just a bridge column that had some issues with honeycomb void being tested on a grid, 1-foot grid, north-south and east-west with light lithium grease spots. Relatively non-staining. If you're really worried about staining your concrete, you use a ultrasonic industrial or medical ultrasound gel, which is non-staining. But here we were looking at how much honeycomb was there present. So as mentioned earlier, the sonic pulse velocity test is used on large structures like bridge piers and dams. So the test has been around quite a while. Leslie and Cheeseman in 1949 came up with this table to characterize concrete condition in a general sense based on ultrasonic pulse velocity speed of sound, the compressional wave. So above 15,000, excellent quality, very high strength concrete. Good quality concrete, good to very good, 12 to 15,000. Questionable, 10 to 12,000. And poor quality, 7 to 10,000, below 7,000. And remember, surface wave velocity is 56% of the compressional pulse velocity for concrete with a Poisson's ratio of 0.2. So in the test, on a small specimen, you can just send the results right through it, directly testing with ultrasound, semi-direct at an angle, testing on the surface, but there you're only really sensitive to the first inch or two of the concrete, and we would tend to use spectral analysis surface waves because it tells you velocity versus depth or wavelength in the concrete. It's a simple test in the sense that the pulse velocity is equal to the distance traveled divided by the wave travel time. There's a general correlation referenced first in 228.1R89, an older document of the ACI committee, that the concrete strength F prime C is proportional to Young's modulus squared is proportional to velocity to the fourth power. But to really apply this, you have to calibrate with cores or cylinders. Otherwise, you just know concrete is relatively strong or relatively weak and don't have a good sense of the accuracy of your strength estimate. And that's true for the Schmidt rebound hammer and others too. Unless you calibrate it to crushing cylinders or cores, you don't have a correlation that's approved by ACI to predict strength. So with the small ultrasonic transducers, you grease couple them lightly, put them on a calibration bar to get these, which has a known travel time. You calibrate your system per the STM standard for testing, say, cores in the laboratory, and then crushing them to get a precise measurement to 1/10 of a millionth of a second of the time required on your testing. So the sonic pulse velocity is a low frequency, high energy version of ultrasonic pulse velocity. You'd usually use an instrument hammer or a steel hammer and a sensor nearby, like the pulse velocity transducer as a source, and then a receiver similar on the other side. As it's mentioned, you can use 2 of these ultrasonic pulse velocity transducers and a simple hammer to do the testing. So here's an example of using an instrumented hammer, which is shown on the right. This pulse is the hammer. That can be calibrated to be pounds force, but here we're interested in timing. And then you look for the arrival time. And then it's 8 feet away, in this case from the impact point. The math says it is 13,889 or 900 feet per second. So that's the calculation. So this all leads up to acoustic sonic dam tomography. This is something that involves measuring the compression, or it could be done with shear waves, but typically it's compression waves, of the velocity of sonic waves are traveling on a mesh of paths through the dam interior. So you can get 2D slices, even 3D images, if warranted, of the velocity profile of the dam. And the faster it is, it's stronger. And if you have no damage, you'll see that as well. Low velocity areas are zones of weak, cracked, or otherwise degraded concrete. So on a dam, it's easiest to do this testing when you have a full pool behind it. So that allows the hydrophones to be used on the upstream face underwater to pick up the sonic wave energy. The wave source on the downstream face can be from climbers with typically 3-pound impulse hammer, or a remotely operated impactor if it's really good condition dam concrete, as you'll see. So this just shows a few projects. It can be done on small or large concrete dams. Again, climbing is often involved on the downstream face. This shows a project, though, where the dam concrete was in good condition and access was very difficult. So we were able to lower down a frame with an instrumented electrical solenoid impact source that we could put at different positions with the tape to generate the wave energy, and then had hydrophones underwater on the other side of the upstream face of this dam. So more typically, the concrete is degraded to the point where such a small impactor will not work well. It's about a 0.2-pound impactor driven by a solenoid, kind of like a door lock. But here is a 3-pound impulse hammer with a hard plastic tip being used by a climber to hit the concrete, typically about every 3 feet or meter, depending on the scale desired, matching up with the hydrophone receivers on the upstream side, impacting on the downstream side. So what does tomography mean? Most of us have heard of CAT scans, computed axial tomography used in medicine, where you're sending X-ray radiation through, and you're measuring the amplitude of the radiation to image the conditions in the human body. Well, this is velocity tomography or travel time tomography. So you can analyze it two ways. If you had a column shape, you could test at a variety of angles, and with these crossing ray paths, you mathematically solve for each of these pixels. What is the velocity of that pixel to match your data? You can allow the physics, which is real, to bend the waves through there because the wave energy will find the fastest path. If it has to go around some damage, it'll go around it, and it's a curved ray approach or bending ray. So that's just something in the analysis software that lets you start off with straight ray analyses where they have to travel in straight lines, but then you allow them to bend and find the fastest path. They're usually similar, but that's just part of the analysis approach. So I hope this diagram helps you to visualize what I'm talking about. Here is the upstream side of the dam with the water high level. These are hydrophones, typically spaced 3 feet apart, could be a meter apart. And you would have typically 8 to 12 hydrophones in a string. And then you impact on a similar grid on the downstream face. So it's very important that you know both the geometry and thickness in a 2D sense for this 2D tomogram of the dam itself and where you've impacted it and where the receivers are. So you tie all that together. So the first time we did sonic cross dam tomography was on a project back east where they were concerned to check the integrity of the dam for safety purposes. And we did 24 2D cross sections on this 480-foot dam length. So every 20 feet along it, here's the spillway and the taller part of the dam to the left, in 5 field days. So it actually went very efficiently. And part of that was because, again, the downstream dam face was smooth, pretty good concrete. So we could build up the frame. You could perhaps see a little better here, these impulse force transducer and the solenoid that drove it. So when we would push the button, we'd hit it typically 4 times at a given elevation and record the response of the hydrophones that were underwater on the upstream dam face. Here you can see it on the dam. Here's another view of that, and looking down on it from above. We never dropped it in the water, which is fortunate, but it's, in terms of safety for personnel, obviously this was not as concerning as having a climber over the edge. Fortunately, we've had very good climbing companies assist us, and one of our engineers is a certified Sprat climber, so he can go over the edge, so to speak, when needed. So this is just on the boat we were using, a picture of the hydrophones looped in a cable. There's a hydrophone. And these hydrophones are spaced 3 feet apart, hung over the edge. There were 8 of them in that string. And there again is the impactor from the solenoid source. We floated around in a boat, took it with an early version of our Freedom PC, and took all the data, and it was done very efficiently. I give our field people very good credit for getting this done. So the mesh or Raypath density plots show why, with many crossing ray paths of the source on the downstream side, the receivers, the hydrophone receivers underwater upstream, that you can analyze this data and determine mathematically which pixels should be faster or slower to match your data with these crossing ray paths. The only place you don't get that, and it becomes just an average velocity, is at the top, where you have very little crossing ray paths, if any, and bottom. Again, very few crossing ray paths. So those become just average velocity results. So some of the data, the way it looked, was this is time and voltage. The compressional wave arrived here, the primary wave, and we even saw a shear wave come in from those impacts. That was used sometimes. There was a little bit of noise because of some drainage through the dam and some grates that was going on. So where that got noisy, we used the shear wave and corrected it to be a compressional wave velocity. But generally, we could see the P wave by averaging out some of the background noise. You can see a little bit of that lower frequency noise still left. So what did we get? We got 24 tomograms, but one of the more interesting ones was this one. From here, you've got anomaly about from 8 on the scale to 48 feet. the receiver position shown upstream, the hydrophones, the source impact points shown. You can see generally reasonable velocity, 10,000 to above 12,000 feet per second for this older concrete. But there's one area that was interesting because it looked like a crack. So this green zone with an even slower velocity, and it showed up with the crossing Raypath. And interestingly enough, the divers went down and confirmed that this was a degraded copper water stop that was embedded in the concrete. So an open joint, if you will. So sometimes your dam concrete can be severely affected by freeze-thaw damage. And this is an example of that where the larger impact impulse hammer was definitely needed. And again, you can see on the right, the grid that was used on this project, again, providing very dense coverage that could be analyzed by the tomography software. So that software produced this plot, which showed significant freeze-thaw damage here, and then it shifted to even the upstream face, because in the wintertime, this portion that the reservoir was drawn down was exposed for freeze-thaw cycles. But generally, it was on the downstream face where that was more prevalent for the damage. And you can see the velocity scale in thousands of feet per second, much slower in damage in portions of this dam. So this allows engineers to figure out the repair approaches, what needs to be done, how serious is the problem relative to dam safety. You can certainly, just a display of multiple 2D tomograms put together to show, and the blue areas are the slower upper portion of this dam had extensive freeze-thaw cracking damage. But you can get multiple tomograms and display them all together if need be. So what are the advantages and disadvantages of sonic cross-dam tomography? Well, you can image internal flaws in a 2D fashion, even a 3D fashion if you take the time to go between those adjacent 2D tomograms. So you can do angled and direct tests. Picture's worth 1,000 words, and the velocity tomograms are giving us images of the internal void, the cracking, any other concrete damage defect conditions. So shifting gears again, now we're going to talk about a common question around spillways of dams is, what's the subgrade support? So we generally combine both slab impulse response and ground penetrating radar to evaluate subgrade support conditions below spillways. So it can also be done on roadways, building slabs, tunnel liners, pipe walls, rigid concrete pavements, combining the same techniques. So there is an ASTM standard. It's also in the ACI 228 document for the slab impulse response method. It involves on a flat slab, a pavement, an impulse hammer, and a geophone. The void below a slab, in a simple sense, you're doing a dynamic stiffness test by measuring the impact force and measuring the vibration response with the impulse response test. It's a modal vibration test. This is that type of equipment. A void will be more flexible and less stiff. And it's sensitive up to about 2 feet thick for impulse response. Then it gets to be too thick in the concrete. So the slab impulse response equipment is shown here. It can also be in the NDE 360. If you have a slab that slopes more than 10%, then the normal 4.5 hertz geophone will not work so well because it's a coil magnet system. And we switch to an integrated accelerometer by Wilcoxon that's also a velocity transducer like the geophone, but this can work at any angle. So from testing a wall, a tunnel lining, a sloping, more severely sloping spillway, we will use the Wilcoxon transducer instead of a simple geophone. So that's the basics of the test. It complements the GPR. It finds very thin voids, less than 1/16 of an inch thick, where ground penetrating radar generally requires at least 1/4 inch, if not a 1/2 inch of void below the slab to see it clearly. So what are we doing? Well, first you measure the velocity response of the slab with the geophone or the Wilcoxon velocity transducer. So you get a result in the velocity time domain. You do an FFT of the signal, and you get the spectrum in velocity. The second thing you've done is measure the impulse hammer. Might be a typical 3,000 pound force, looks kind of like a half sine pulse for just only 2 thousandths of a second, 2 milliseconds. So This result becomes again a spectrum, which goes to the frequency domain with an FFT of the fast Fourier transform. Typically doesn't excite much above 2000 hertz. So then you do the transfer function calculation. And this is called mobility when you're looking at velocity divided by force of the two spectra. So you measure the force as a function of frequency from the hammer. You measure the velocity as a function of frequency from the geophone to calculate the transfer function or mobility, which is velocity over force versus frequency. We also use the flexibility transfer function. It's simply integrated from velocity to displacement in the data. But now you're looking at flexibility, which is displacement over force. Well, the inverse of that is force over displacement, which is stiffness. So you go from inches per pound force in calibrated systems, which you want to be, to stiffness, the inverse of flexibility, pounds force per inch, kind of like a spring stiffness or a subgrade stiffness coefficient for the system. So the application of these two methods is illustrated in this case history, where we combine slab impulse response with ground penetrating radar and used a video borescope in core holes to further look at predicted support conditions below this spillway slab on grade. We're going to talk about the project background, how we designed the surveys, how we combined the results, example results, and the core hole ground truthing that was done. So it's a mountain spillway. You can see here that it's sloping down. It's about 3,000 meters, 10,000 feet above sea level. Pretty good sized, not enormous, but 46 meters long by 15 meters wide at the top, tapering to 10 meters wide at the bottom. And it ranged in thickness from 7 to 14 inches. And it had 1 mat of steel and nominally a 12-inch spacing. The reasons for the project to be done with non-destructive testing and evaluation is the engineers had observed water seepage at the joints and concrete spalling. They'd done some hammer sounding and it was hollow sounding, which you can't always do through 7 inches concrete, but it sounded hollow to them. In bridge decks, we think you can hear hollow sounds from corrosion and delamination down to about 3 inches, and then it's hard to hear deeper than that. And some limited drilling had shown that there was indeed void or subgrade void below the spillway. So the methods we used are shown here on the right: ground penetrating radar with a distance wheel and an electromagnetic 400 megahertz antenna. And then that's the Wilcoxon velocity transducer and the 3-pound hammer that was used for the slab impulse response testing on a grid basis. So the slab IR was done on a 4x4 foot grid with 3 hammer impacts were collected at each point, and the response is the velocity transducer. 428 data points total. Took about a day and a half to do that on the spillway and about a day and a half to complete the radar because of the slope. And so we ran these lines, did the testing on this grid. Here's a hammer signal. That's about 5,000 pounds of force in the time domain. This is a receiver signal that's actually ringing, which is indicative of void below the slab because the slab is not damping out. It could be a lot smoother and damp out very quickly with good sound subgrade support. So then we were using this to calculate the mobility. The plot on the upper right is good subgrade support. This is mobility in inches per second per pound force. A little hard to see that scale, but very flat. This is typical of good support. And the coherence is very high, near 1. This means the signal to noise ratio, when coherence is near 1, is very good quality data, very repeatable. So we get the mean mobility out this, the shape of the plot, and the initial slope at low frequency is the flexibility of the plot, which we can also plot in another part of the software. By comparison, a poor subgrade support area, possible likely void, had this much higher, same scales, irregular mobility. So it's not damped, and the velocity over force is much higher, meaning you get a lot more vibration amplitude per unit force versus frequency from 0 to 1,000 hertz than this sound good subgrade support area. Very flat. And the coherence was a little more ragged as well. But what was critical is the fact it was so much more mobile and much more flexible, less stiff than the good support area for a similar thickness. So then we also did ground penetrating radar on the project. We do almost always do the methods together because they're complementary. And basics of radar, as you move your antenna along, you'll see rebar quite well. It reflects from that change in dielectric constant. So the amplitude of the reflection is defined by the upper dielectric constant of the material, and this is called relative dielectric constant, to the square root power, to the 0.5 power, minus the lower, in this case it would be air void, to the square root, divided by the sum of the two, both to the square root. That's how much of your radio wave, your electromagnetic wave gets reflected. So we were interested in that because we were checking for void. So the raw data, which you don't normally see, you can see it, but is shown here for a single pulse. And this is time in nanoseconds. And as it goes down, you see the reflection in time from the top of the concrete surface. It continues through it. If there was a rebar, you'd see another reflection in the middle. There's not. The bottom of the slab is right here, the second reflection. So if you know you can get the electromagnetic wave velocity by either knowing the thickness of the slab or from curve fitting, as I'll mention in a minute, of the data over rebar. But it's equal to the speed of our wave times the reflection time over 2. Typical dielectric for concrete is around 6. It varies. Could be up to 9 or more, but typically around 6 if it's drier. So as you scan along, and you had a buried object, in this case, we are going over a rebar. As you come along, you kind of see the tail of it first because the radar wave spreads out. When you're right over it is the center of the rebar, and then as you go by it, it goes away. And that hyperbolic shape can be used to get the velocity of the wave in that material. So you can, in essence, curve fit it. So if you had a corrosion issue, which is used some, it's not as reliable as some other techniques we use for finding corrosion damage, like impact echo scanning on bridge decks, but you get a fuzzy, weaker, lower amplitude signal when a bar is rusting and corroding versus a clean echo from a non-corroding rebar. And here the antenna is moving along with a transmitter and a receiver. You're actually picking up with that geometry, these so-called bow tie antennas, you're crossing over these rebars. So you're going over them. You can see a little bit of banding here that could be attributed to if you're right over the longitudinal rebar, but that doesn't show up as well as going across it for mapping rebar. So you would scan 2 directions if you wanted to see the other steel better. So some relative dielectric constants are shown here for different materials. Concrete shown as 8 to 10. A lot of times we found it to be 6, at least in Colorado. And sands, gravels, clays. If it gets too clay and too conductive, you can't see deeper. You can lose the signal. If you have plate steel, you won't see the signal. If you have too much rebar, you won't see deeper. So on the spillway, it was reinforced. We did use a safety rope and backed our way down with the wheel. On a 4-foot grid, we used some similar to the slab IR, except that was a 4x4 foot grid. This is continuous scanning with 106 pulses per meter of the antenna. So we get a lot of data. This shows that radar grid. It was broken up into 2 sections for the lower portion of the spillway and the upper, which is on the right. This shows some example data from the lower part of it, I believe, that here we're going from 70 feet to 105 feet along one scan line. The concrete to soil interface is here. Where it gets into the brighter colors, that's actually a stronger reflection indicating void below the slab, the spillway slab. You can see certainly how the rebar is going up and down. All these little hyperbolas are going up and down, and that can be calibrated to be actual depth, which is shown on the right. So this is showing 0, half foot, a foot deep versus travel time, reflection time on the left. So we found a number of spots with void. The reflection coefficient of void was half the energy coming back, 0.52, versus soil about 0.22. The bright spots became the likely void areas. So the radar data, combining the results, is in two sections on the left, the upper and lower part of the spillway. The darker color is showing the voiding areas. That correlates pretty well with the slab impulse response. The mean value of 1 was normalized, and as you moved up into these colors, into the blues, it was much more mobile, meaning much more likely to be voided. So you can see there's a general correlation between the two tests as showing void below the spillway slab. Then we suggested coring locations, and based on the white dots to open white circles with dots, the void thickness went from 1/2 inch up to 4.5 inches thick. And then in general, some of the worst areas also had the deepest voids from the physical testing. Neither test is generally going to give you the thickness of the void. That comes out of coring or drilling and probing. So we did take the cores, and we had a borescope that was a very sophisticated one. You can actually drive it with a joystick, so we could go in a hole and take pictures below the slab. And we confirmed they were voids, and it could go out about 10 feet from a given core hole location to see conditions. So a successful project, and they were able to recommend the slab grouting type repairs to restore the spillway support. So another example of GPR is just scanning. You can do structures with it, you can do pavements with it, you can even get ice thicknesses with it. Here we are scanning a soil cement liner of an embankment dam looking for voids below it. And this just shows pulling the same wheel along, 48 scans per foot. It could be done top to bottom or on a given horizontal line in a given elevation around the perimeter. We scanned quite a bit of it, 2.5 miles of liner was scanned. What we saw, here is the slab top. Here is a small void showing up in this area. This is showing much brighter, stronger reflections, a larger void area. It was checked with a core. This is core number 9 location for that particular voiding area. So these bright spots, again, were showing below this soil cement where this embankment, which was built of sand, compacted sand, was no longer in contact with the soil cement liner. So this shows that you take the cores out of it. Interesting enough, most of the time we got the cores recovered just fine. Really big voids, the core stayed in the hole through that soil cement liner, but you could still measure it and confirm the thickness of the void. It was just proof positive, and indeed there was a problem. So it correlated very well, again, helping to assist in remediation efforts. So the final thing I'm going to close with today is infrared tomography. This is the idea of using an infrared camera. Many of you have seen these cameras. You can even get them on an iPhone nowadays from FLIR or on an Android phone. There's an ASTM standard for using it to detect delaminations in bridge decks using infrared tomography. The basic idea is the anomaly, the crack or the delamination, will produce a change in the apparent surface temperature of the concrete. So here's the infrared camera. Here is an area that's delaminated, say it was a bridge deck corroding or debonding of overlays and patching materials. That thinner piece of concrete has less thermal mass. It will heat up faster in the morning with sunshine and cool down faster in the evening than the normal thicker concrete. So we did this on a cyclopean masonry dam spillway that had had some cementitious patching repairs for a few inches in thickness. We also did surface waves and sonic dam tomography and some impact echo testing to characterize the conditions of the old dam. But the infrared was most of interest for this talk today because at the crest, there's some really higher temperatures. You have to have sunshine for this test to work. As it warms up in the morning, you will typically see the changes in temperatures. And so even though the whitish areas are the hottest, there's also yellow-orange areas are also showing debonding or delamination. And the cameras will give you a picture of what you're taking the infrared picture of as well as a normal visual picture. So you compare them side by side. The staining will make it look warmer as well. You can kind of see that here with this staining and this staining being warmer because it's darker. So on the downstream face, here's the view, and you can see efflorescence between the joints of this older cyclopean masonry dam. but there's quite a bit of delamination of the patching material that had been applied. So it can be very useful where this is the issue to find shallow cracking. It won't see more than say 2 to 3 inches deep. It's only sensitive to problems in the first few inches. So it's simple and easy to train. It's easy to detect shallow anomalies, difficult to detect anything deeper, and you get the photograph along with the infrared image. But you do have to have sunshine and a change in heat. So you definitely have to have a good sunny day, check the weather forecast. So to summarize, there's the methods are listed here that we've gone over today. A general application guide is given to show on stress wave methods for material integrity and deterioration of concrete, masonry, and steel materials even. Impact echo, surface waves, pulse velocity for tomography, slab impulse response for subgrade support, and ultrasonic pulse echo or impact echo can be done for corrosion and bolt integrity links, which I didn't touch on today. But also we did touch on pulse echo for corrosion. Certainly the GPR and modal vibration methods for mapping out, again, the subgrade support. And finally, infrared thermography for shallow concrete delamination mapping. So it's certainly been a pleasure to talk to everyone today. If you would like to send me an email personally, it was listed at the start as larry.olson@olsonengineering.com, or you can send it to our corporate email of info@olsonengineering.com. So if you have any potential project questions, any technical questions, we'd be more than happy to talk to you about them. We have both a Washington, D.C. area office in Rockville, Maryland, and the main office is here in Wheat Ridge, Colorado, which is the west side of Denver by Golden. We will be posting this, as I mentioned earlier, as a YouTube video downloadable, probably within a day or less, and send an email to everybody to follow up on this. And then you can also download the slides from a link at the YouTube site or from the Olson Engineering site under Services and Training, where the webinar PDFs are listed. I'd be happy to take any questions now, and I'll turn it over to Ryan to kind of tell me if there's any chat room questions. And thank you again very much for your time today.
All right. The first question is, which method or combination of methods is best for testing for defects in a thick 2.5 meter element, a smooth accessible surface, and an irregular inaccessible surface?
Okay, given that, I would recommend the combination of impact echo and surface waves, but with larger hammer in using the accelerometers to see deeper, because 2.5 meters is nominally 8 feet in thickness. A little more than that, in fact, approaching like 7.5. Yeah, pretty close, 8.5. So I think those two tests will do a good job, done on a good grid basis. It also depends on the size of the anomaly that you want to find.
We have also used corrosion rates and electrochemical potential mapping in dams looking for corrosion. Do you have any comments on these methods, which are also in ACI 228?
Yeah, we've used the galvanostatic pulse approach in our own work where there is rebar corrosion. Generally, you have to touch. We've also used electrical impedance spectroscopy for some unique applications. But you generally need to contact the steel. You'll get the half cell potential, the concrete resistance, as well as a rough estimate of the corrosion rate. It better be, as you probably appreciate, above freezing, meaning 35 degrees or warmer for the corrosion activity to be going on. And we found it to be reasonably good. As far as corrosion rate estimation goes, you should do that seasonally. It won't be that accurate. Studies have shown it'll estimate the rate with an accuracy of, say, 0.3 to 3 times the true corrosion rate with the galvanostatic pulse equipment. The G-core type equipment, which is similar, but it's induced polarization, is more erratic. It will probably go from a 100th to times 100 accuracy. So I saw that from a researcher at an ACI meeting who had done it at the University of Toronto, I believe.
There's another question about how do you deal with thicker section scannings with GPR? I think they're asking what's the thickness limit?
Well, it all depends, like one of those answers. But basically, with most structural antennas are between nominally 1.5 and say 2.7 gigahertz. And those antennas will generally see in the range of 1.5 feet to at most 2 feet into the concrete, assuming you don't have a lot of rebar that is reflecting the energy. You can go to lower frequencies like 900, 800, 400 on down to 200, even 100, and see much deeper, but you will lose resolution. So it depends on what you're looking for as to that combination. And there are some suppliers now that combine 2 antennas or step them over a frequency range. So Ryan may want to comment on this because he's done an awful lot of ground penetrating radar as well.
The only comment I'll make on thickness is when you're scanning through a slab, there's almost always some reinforcement. So it's a constant optimization problem of what frequency will image through the reinforcement and still see the target of interest. Usually you have lower limits. If you're below a 400 megahertz antenna, a lot of times you just won't be able to image through the supporting mesh. And for higher frequencies, you'll get better resolution, but you just won't have as much penetration. So it's a trade-off, and there's no perfect answer.
Yeah, that was Dr. Ryan North, our principal geophysicist, and he gave a talk earlier that you could see along with Travis Nielsen, did a lot too on the seismic geophysics at the YouTube website. Thanks, Ryan.
All right, so the next question was, have you had any success defining shear wave onset with hydrophones?
We have seen on the cross-dam tomography, that example result I showed of the shear wave is actually a true shear wave traveling through the solid concrete dam that was mode converted to compressional wave and showed up quite clearly because the hydrophone was right against the concrete. So in that sense, we saw the shear wave emerging into the water. As you know, the shear waves will not propagate in water. I hope that answers the question. I'm not sure I totally got it, but I think that's what you're asking.
I was going to follow up with that with saying that it is possible to make a measurement on a surface of shear wave if there is sufficient coupling between the sensor and the wall, but the energy is not going to propagate through the water. So again, like many of these, it depends. All right, so the next question says, what is the accuracy of impact echo testing on a wall on the seaside?
On the seaside, meaning an ocean?
I assume that means on the wet side of a dam structure if you use maybe the submersible IE sensor.
We have had divers go down on bridge piers underwater and to check the extent of cracking damage due to the ship impacts to the bridge piers. And it worked quite well. You will see in about up to 6 feet. It's very well coupled because of the water. Just as always, you have to make sure that the transducer of that waterproofed IE-1 test head I showed earlier is held in good contact and a good blow is applied, typically with a round end of, say, depending on thickness, a 4-ounce to 2-pound ball peen hammer. So you can penetrate quite a bit. But when we do that, we're always doing surface waves as well because it'll go across the cracks and tell us the depth of a perpendicular crack and the severity of the cracking. Again, we can spread that out to about 2.62 feet. And again, using maybe a 8-ounce ball peen hammer as a source. So we would combine both tests. We certainly have done ultrasound underwater. Our ultrasonic transducers go underwater. That can work very well because of the coupling, but if it gets to be too thick, you're back to doing sonic pulse velocity with a normal hammer impact. And we generally would not take an instrumented hammer underwater. I guess we could maybe waterproof it, but we'd probably use a couple of ultrasonic pulse velocity transducers and hit with a steel hammer if we were doing sonic pulse velocity or tomography. In some very unique cases, we've strapped tubes on bridge piers and did cross-hole sonic logging and tomography.
All right, next question is, I think, of the methods you've discussed, what's your suggestion for detecting delamination between concrete layers, new concrete on old concrete?
Two, depending on the situation. Impact echo works well. The research has shown that if you lose about 25% of the contact condition across a crack or a layer, that you will see a resonant echo if you can excite it and it's within your measurement range of, say, 3 inches to 6 feet. The surface waves can work very well for delaminations, surprisingly. when you lose even more contact, it will find a delamination because it shows up as a reduction in velocity. And we've used that to also find delaminations. Slab impulse response, if it's within 2 feet or less, can show the degree of bonding to an extent because you're getting the stiffness response. And if it's not well bonded, starts to be like a debonded cold joint, it will be more flexible and more mobile. So those 3 methods are the ones that could be used for that application. Oh, if you're really scanning a big slab, I don't think of it that way often. We actually have a slow rolling sonic surface scanner. You can see in the talk I gave on bridge evaluation back in May, that's also on the YouTube website. This allows you to do both slow rolling impact echo and surface wave tests every 6 inches on 2 wheels, walking a mile, mile and a half an hour. And it could work well on a spillway because it was designed for bridge deck damage mapping.
Okay, another question asked about slab impulse response as a method on itself. What are the other applications of that in addition to void detection?
It is referenced in ASTM and it can be used for structural integrity evaluation. It's sort of an overall dynamic stiffness test. And so if you had void and honeycomb and some of these debonding issues or cracking, it will detect it, but maybe not define the actual damage as well as impact echo and surface waves can. Or another similar test called ultrasonic pulse echo, which uses shear wave transducers.
Okay, what is the maximum thickness of a slab that you can test with the impact echo method?
We've gone to 12 feet, but then we switched to accelerometers and really big hammers. But you're not going to detect much defects in the sense of it's about 0.6 times the depth it spreads out. So your defect detection will not be very good at 12 feet at all in terms of anything smaller. But in terms of thickness, it'll work well to at least that thickness that we've done in our own work.
So there's a couple of questions on using GPR to detect reinforcement diameter. If you don't mind, I just answer that one saying that you can't really do that with commercially available GPR. There are 10, 20 papers out there that show proof of concept that it can be done with much higher frequencies, typically in the sort of 3 to 7 gigahertz range, but most commercial GPRs top out at below 3 gigahertz. So that is not a suggested method for determining diameter. And probably the most common method for determining diameter is a cover meter, which is just a time domain electromagnetic induction instrument that by measuring the amplitude and the decay of that amplitude of the response can be correlated to diameter. So then the next question is, what is the accuracy of SASW and how do we avoid higher modes during processing?
Well, it depends on what you're doing. You're definitely going to get some higher modes. The issue is that it's somewhat dealt with in the latest multi-channel analysis of surface wave software. Dr. Stokey and Rosette put in a rough approximation theoretically for higher modes of the earlier WinSASW software that I learned on. And I've used the newer software a bit myself. But a gentleman named Dr. Nils Ryden from Sweden addressed this specifically for the difficult problem of going on a concrete pavement and determining the surface wave, shear wave velocity, shear modulus of the underlying road base and subgrade. And he did that by modeling specifically the higher modes. So it can be done. It hasn't become so commercialized yet. We're working on it. Some other folks are looking at it. So you can deal with it. But it's a good question. In terms of what I was showing, and for the concrete application, it's not such an issue because it's not the severe contrast you get into in a concrete pavement of going from the very fast concrete to the thin, much slower road base layer on into the soil subgrade. Hope that helps a little. But feel free to send me an email and I'm happy to give you some of those references and talk about it further.
All right, what is the sampling rate for impact echo testing and how will the sampling rate affect your accuracy?
It's a question in the basic digital sampling. We typically do, say, for most routine work, 10 microseconds per point, which gives us a Nyquist frequency up to 50,000 hertz, which practically speaking means we would see a resonant echo, which is hard to excite, at about 1.5 inches thickness. So as long as your sampling puts your Nyquist frequency above, which is half of your sampling frequency of 100,000 samples a second or 10 microseconds per point, as long as you're not exciting energy above that, you don't get into any of the aliasing problems or anything else, then it's a question of how do you excite it. We use a lot of solenoids for most of our work, from say nominally 3-inch depths up to 18 inches maybe. And then we start to use the hammers to go to lower frequencies. So you can, as long as you don't violate those things, that's a good general rule of thumb. And maybe we would take 2048 points. As you take more data points, then you get a finer delta F. That's the other factor here. And for example, on the 50,000 hertz, we would then have a resolution of 50 hertz on the points with that sampling, which is very good. But again, it depends on your echo. So if you had a 6,000 hertz 1-foot echo, you had an accuracy of plus or minus 50 hertz, that's within 1% roughly, and that's very good as far as depth goes.
There's a GPR question about phase relationships between your received response and conductivity of the structure.
I'll let Ryan take it. I could deal with it, but I think he's done an awful lot of research and work in his former position with the Army Corps of Engineers on radar.
So generally, measuring in situ attenuation is quite difficult in GPR, and the attenuation is the function of the conductivity. There are a handful of publications looking at this, but there's no standard field method for extracting conductivity information or the attenuation in decibels per meter from the data. There are some people that have looked at doing that with specific geometries, but it's not a simple problem. Next is a question about GPR detecting leakage from concrete tanks containing water. Yes, you can do that. You're gonna see an amplitude reflection response in areas that are saturated versus areas that are unsaturated and partially saturated. So next question is, what do you recommend for concrete defect detection where there is an asphalt overlay, and does having the asphalt overlay make it easier or harder?
You definitely want to take a look, if you can, at the YouTube for Olson Engineering, because in the bridge deck portion of that, we've done research on both asphalt pavements and asphalt overlaid bridge decks using impact echo and surface waves. And the surface wave technique is able to discriminate between a debonded asphalt based on wavelength and a drop in velocity at that depth. A greater wavelength would be a delamination or corrosion induced at the plane of the top deck steel. And even greater, we've seen a bottom steel delamination also result in its velocity drop. But it can be done using surface waves primarily. And that gets back to the sonic surface scanner I mentioned, which is kind of like a radar cart, where we would be rolling these wheels with solenoid impactors and displacement transducers that test every 6 inches, typically spaced 6 inches apart on a typical asphalt overlay deck or pavement to find debonding of the asphalt pavement lifts, if that's the concern. So we've documented that both in some research and papers. And so if you want to send an email or take a look at the bridge deck webinar or the PDF of that talk, that's where I would point you as well. But thanks for the question.
What is your opinion on the pulse echo tomography method for delamination detection?
I think the ultrasonic pulse echo is a good technology. There's 2 commercial systems out there, distributed in the US by Garmin Instruments, the Mira system, and then the ProSec system. And they both work well. They're using ultrasonic shear wave transducers. You have to push the unit against the concrete and hold it, so it's not quite like scanning, as we do in some of our impact echo work. But certainly there's nothing wrong with technology. I don't think it's going to work too much beyond, say, 3 feet to a meter in that regard.
Okay, what is the method you propose to find the source of water leaking in a tunnel? And then there's a secondary question of how the chloride content of the concrete affects the wave speed.
Well, the chloride content will not affect the stress wave speed much at all. It will have some attenuating effects. And that's one of the problems of the ground penetrating radar on asphalt overlaid decks, is you can get into issues with seeing the debonded asphalt, the icing salts at different layers, and complicates finding corrosion. using GPR on an asphalt overlaid deck. You can do it, and we've tried it, but it's not always the easiest. And Ryan may want to add some to this too, because I think part of this is radar.
Actually, for leaking, water leaking in a tunnel, I guess the question is are you looking from the inside of a tunnel that's mostly dry and you're looking at water coming in, or the tunnel is fully filled with water and it's leaking out? But generally, looking for leaking water or other liquids usually involves an electrical method, either spontaneous potential, electrical resistivity, or GPR, and each one of those might be a better application depending on the details and the geometry. All right, now I'm going to go to the next question, which is for the impact echo method. Why do you propose having the source 5 to 6 centimeters from the receiver, knowing that the source receiver distance should be 2 times the required depth of investigation?
It has to be less than 2 times the required depth of investigation. So closer is better, but when you get beyond that, so if you had a foot thick, you wouldn't want to hit any further away than 6 inches from your receiver to the source. So by staying that close, practically speaking, in most testing, we don't have to worry about that issue. We want to hit close to the receiver.
All right, so then there's another question. Is there a rule of thumb for frequency versus void size detection for either GPR, pulse velocity, or impact echo, whatever method you're selecting, I guess?
Simple rule of thumb is wavelengths you would like to be less than or equal to the size of the void you want to find. But it very much depends on the path. And as you start to do tomography with more angled paths, you can get a little better discrimination. It is definitely a function of wavelength. The 50 kilohertz transducers is nominally a wavelength in 12,000 foot per second concrete of around 3 to 4 inches. So that's the comment on the sonic side. I'll let Ryan talk about the radar side.
The general rule of thumb for GPR is that you're not going to find anything smaller than a quarter wavelength.
And I think in terms of impact echo, it depends on the nature of the flaw. You can see a change in the impact echo result, but maybe not get a distinct reflection unless it starts to approach like 0.6 times the depth. Then you might get a very distinct reflection. So it does depend on the nature of the flaw, whether it's a tight crack versus a void, it's a planar void versus distributed honeycomb, which will not resonate as well, but overall look thicker in the result.
There's a question about leak detection. It says, what's the possibility of half cell detection? Same principles of self-potential methods. I guess to clarify, those are exactly the same thing. So yes, there are ways that you can use self-potential method to identify leaks just based on having a closed current path loop. And you can use that as one approach for finding leaks in, for example, a pond, retention pond for like mine waste if there's a hole in it. But there are ways to do that for using these electrical methods to find leaks. I don't know if that answered the question or not. But that appears to be the last question. If there are any questions that were missed, please send an email to the info@olsonengineering.com email address, and we will address those for you, and then I'll let Larry close.
Yeah, and I certainly want to thank everyone for attending. The 85 of you have stuck through or so of this question session as well. We're happy to answer further questions. Just send us an email, and I really do appreciate you're taking time out of your day to attend the webinar today. We'll be giving more webinars in the future, so we'll keep you posted. And as we're all saying, stay healthy, and I hope everybody's back working. Have a good day.